Now that we know SOHCAHTOA, we can apply this principle to solving right triangles. When we find the measures of the 3 sides and 3 angles of a right triangle, it's called solving the triangle. The ability to solve triangles is very useful for all sorts of mathematical applications. For example, you may use this in architecture, in surveying, or in engineering. So it's a very useful skill. You may have even had to use SOHCAHTOA and solve a triangle when doing home improvement projects. Who knows? So let's talk about the strategy for solving a right triangle. The acute angles of a right triangle are conventionally named alpha and beta, and the lengths of the sides opposite those angles are then A and B respectively. So if we imagine a right triangle, in general, we name the angles alpha and beta, and the right angle is represented by the Greek letter gamma. Opposite angle alpha, we label that side A. Opposite angle B, we use the English counterpart to the Greek beta to get B. And the side opposite gamma, or the hypotenuse, we call C. To solve a right triangle, we can generally use the Pythagorean Theorem to find the third side when 2 sides are known. Then we can use our newly learned SOHCAHTOA strategy to find missing sides or angles, and that's sometimes in combination with those inverse trigonometric functions. And number 3, remember always that the sum of the 3 measures in a right triangle is always 180 degrees, at least when you're working in Euclidean spaces or flat spaces. It's another story for spherical trigonometry, or triangles on the surface of a sphere. So we're going to stick with traditional geometry. The sum of the 3 measures in a right triangle is always 180 degrees. So let's use these principles to see if we can solve the triangle given here in example 4. Solve the right triangle in which A equals 10 and C equals 12. So we know 2 parts of the triangle, and we need 6 altogether. Notice we're given the freedom to round angles to the nearest 1/10 of a degree. That means they're not going to come out to be nice common angles. So I'm going to go ahead and label this conventionally. This is alpha, this is beta, this is gamma, or the right angle. The side opposite angle alpha is side A, and we know that's going to be 10. The side opposite the right angle is the hypotenuse. We label that C, that's 12. So we don't know alpha, beta, or B. So we need to start by finding that segment B. And we can do that with Pythagorean Theorem. So the sum of the squares of the legs of the right triangle is equal to the square of the hypotenuse. Make sure when you set up Pythagorean Theorem that the 2 legs are on one side of the equation. Remember, the legs frame the right angle, and the hypotenuse is always by itself. If you transpose those terms, your numbers won't come out correctly. Let's go ahead and square these values. We get b squared plus 100 equals 144. Subtract 100 both sides. We get b squared equals 44. We'll take the square root of both sides. I'm going to think about the square root of 44 as the square root of 4 times 11. So we can see square root of 4 is 2, and 11 does not simplify. That's the exact value. Notice I am not rounding here. Since I'm able to calculate an exact value, I'm going to leave it as an exact value. The only thing that I want to round here on this problem are the angles. So now we know the 3 sides of the right triangle, with the side B being equivalent to 2 square root of 11. Next, we need to find the angles of the right triangle. Let's start with alpha. Notice alpha, we know all 3 sides of that right triangle. So we could use either sine, cosine, or tangent to find alpha. Because I want to avoid that radical, I'm going to use sine. Okay, so sine of angle alpha is so, opposite over hypotenuse. So sine of this angle is going to be equal to the opposite side, which is 10, over the hypotenuse, which is 12. So we need an angle with the sine value of, after we reduce it, 5/6, just reduced by a factor of 2 there. Now we know there's not a common angle that has a sine value of 5/6. Think about the hand trick. It's all numbers like 1/2, square root of 3/2, square root of 2/2, 0, and 1. So alpha is not one of our common angles. So how do we find it? Well, to solve this equation for sine, I'm going to show you all of the steps here. We're going to apply the same operation to both sides. When I apply inverse sine to both sides, on the left we have inverse sine of alpha. Remember, whenever you apply a function and its inverse successively, they reverse each other's actions and you end up with your argument. Okay, now you don't have to show that in full glory every time. I just wanted to take the opportunity to show you that one time. You can go straight from here to here in your work. So the angle alpha is equal to inverse sine of 5/6. We'll approximate that to the nearest tenth with our calculator. Now we want to be sure that our calculator is in degree mode. I know that mine's in degree mode. I've just switched it over. So check and make sure yours is in degree mode. And we'll evaluate inverse sine of 5/6. So the result to the nearest tenth in degrees is 56.4. So alpha is 56.4 degrees. So be sure that you have your degree symbol there and make sure you've rounded to the specific decimal place requested in the problem. So back on our diagram, we can now see alpha is 56.4 degrees. Now, we could do the same thing with beta. We could use a trig function. We could do cosine of beta equals 10/12 and then apply an inverse cosine to get beta. Or it could be a little easier here, since we already know two of the angles. Remember, the sum of the angles in the triangle has to add up to 180 degrees. Gamma is the right angle. We know that's 90 degrees, so we know the sum of alpha and beta must be 90 degrees. So we could say that angle beta then is 90 minus 56.4 degrees. And evaluating that, we would get beta equals 33.6 degrees. So I'm going to go ahead and label this on the triangle. Since all three sides and all three angles have a measure, we have solved the right triangle. And by the way, the little box where angle gamma is, that's sufficient to indicate that that angle has a measure of 90 degrees. So in that problem, we used Pythagorean Theorem, we used a portion of SOHCAHTOA, and we used the fact that the three measures of the angles always add up to 180, and we were able to use those pieces of information to solve the triangle. Let's try example 5. This is going to be reminiscent of some analytic geometry that you learned in college algebra with the new principles of SOHCAHTOA that we've just learned. Example 5 says, solve the triangle whose vertices are located at A, 0, 0, B, 4, 2, and C, 7, negative 4. Give angles to the nearest degree. Let's begin by constructing our triangle. Point A is at ordered pair 0, 0. Point B is at ordered pair 4, 2. And point C is ordered pair 7, negative 4. These three vertices construct a right triangle. So I'm going to go ahead and connect the dots. From the drawing, it appears that angle B is the right angle, but we don't know that for sure yet, so I don't want to make that assumption. We need to solve this triangle. To solve the triangle, we need to find the measures of the three sides and the measures of the three angles. We're going to be able to do that with the distance formula. So again, this is reminiscent of college algebra. So let's find the distance of segment AB. Now, before I do, let me remind you of that distance formula. Remember, the distance between any 2 points is given by the square root of the difference in the x values squared plus the difference in the y values squared. So segment AB then is going to be equal to the difference in the x values. The difference there is 4 and squared plus the difference in the y values squared. So 4 squared is 16, 2 squared is 4. Segment AB has a length of square root of 20, and thinking of that as 4 times 5, segment AB has a length of 2 square root of 5. So I'm going to go ahead and label that on the diagram. We can do that same thing with segment AC. AC is going to be a little easier to work because we're looking at the distance between a point and the origin. So we're going to find the difference in x values. There we'd get 7 and square that. Find the difference in y values. We're going to square that. It's going to come out positive. And evaluate. So 7 squared is 49. 14 squared is 16. That sum is 65. 65 is 5 times 13, so that does not reduce under that radical. So segment AC has length square root of 65. Now the problem did not specifically state that this is a right triangle, so I'm not going to use Pythagorean theorem to find side BC. Pythagorean theorem only works on right triangles. So that I don't make a faulty assumption here, I'm just going to use the distance formula one more time to find the length of segment BC. So this one's going to be a little more work. We're going to find the difference in the x values, 7 minus 4, and square it. We're going to find the difference in the y values, negative 4 and 2, and square that. So it looks like we're going to evaluate 3 squared plus negative 6 squared. That's the square root of 9 plus 36, or the square root of 45. Thinking of 45 as 9 times 5, we can reduce that to 3 square root of 5. So segment BC has length 3 square root of 5. Now we can use these 3 lengths to verify that this is a right triangle. Remember, the hypotenuse is always the longest leg. The longest leg here is longest length here is 65. So let's test it out to see if it obeys Pythagorean theorem. So we're going to see, does segment AB squared plus segment BC squared equal segment AC squared? And I'm going to put a little question mark to show that I'm testing this. So segment AB is 2 square root of 5 in length. Segment BC is 3 square root of 5. And segment AC is square root of 65. And we're going to square all of those. So 2 on this first term, 2 squared is 4. Square root of 5 squared is 5. So the squared value there is 20. Here we get 9 times 5, which is 45. And when we square the square root of 65, looks like we have a right triangle. Since the 3 sides obey Pythagorean theorem, then we do have a right triangle. So it looks like angle gamma, the side opposite, I'm sorry. Yeah, that's right. No, this is unconventionally named. Usually vertex C is opposite the hypotenuse. In this case, it's named B because of the way the problem's set up. So we can say angle beta is 90 degrees. So we've got 2 more angles to determine. I'm going to determine angle alpha next, and I will choose to use the opposite side and the adjacent side for the ease of the fact that those square root of 5s are going to cancel. So if we're using opposite and adjacent, OA, that goes with tangent. So we could make the observation that tangent of angle alpha at vertex A there is opposite 3 square root of 5 over adjacent 2 square root of 5. So then alpha, here's our shortcut, is inverse tangent. After canceling the square root of 5, we get 3/2. So we can pop over to our calculator and evaluate inverse tangent of 3/2. I am in degree mode. Need to think about that every single time. And rounding to the nearest degree, as the problem indicated, we get 56 degrees. So alpha has a measure of 56 degrees. So I'm going to go ahead and label that on my diagram. Then last, at the angle at C, we'll call that gamma. The sum of gamma and alpha should be 56. So we can take the sum of gamma and alpha should be 90 degrees. So I can take 90 degrees minus the angle that we know, 56 degrees. We're going to get 34 degrees for angle gamma. So we have solved the right triangle. What I want you to observe here is that we are finding the lengths of the sides and the measures of those angles without actually measuring anything. We're using principles of mathematics to do that. This is called analytic geometry. We're analyzing the diagram based on the principles we know, Pythagorean Theorem, distance formula, SOHCAHTOA, in order to find those measures without actually physically measuring the object. That's why this type of skill is so useful in surveying, engineering, architecture, construction, all kinds of interesting things. So in the next section, we'll look at applications of these very skills.